My name is Mehdi Khanzadeh. I'm an assistant professor at Temple University. I'm hoping I'm not going to disappoint you after this great talk. So what I'm going to focus basically, it's a research that spans over the last 10 years of my research, starting from my PhD work, postdoc, and some of the current work we are working at the Temple University. So here's the outline for presentation, very small brief background. I'll talk about the three different imaging techniques and X-ray and neutron imaging. And application-wise, probably I'm going to mainly focus on the freestyle and internal curing because of the time, and very short final remarks on how this technique can help for performance plan. So starting with the background, we all know about the durable tissues, right? We can spend the day to talk about each of these, right? And we know the liability and associated with this durable tissues. But what I'm going to focus is kind of common cause between these different durable tissues, and that's the mass transfer, and how we can apply this X-ray neutron imaging to help get more insights about this phenomena in different cementitious material. And since this session is about the characterization, I thought this can be useful really why the characterization is important in concrete or any material. So we have these four different pillars in any advanced materials, right? The structure for that material, the processing, the properties, and finally the performance, right? But the point is we need this advanced characterization technique to kind of combine this and relate and connect these different properties, right? If you want to get a high performance system. And concrete is not exceptional, right? We can fit the concrete in this loop, and we have these different pillars, and advanced characterization can help to understand more about the phenomena happening here. And obviously in this presentation I'm going to more focus on the mass transfer. So about the different imaging techniques, I think the first session which we had a talk related to the microscopy as well as the neutron, so that's a great help for me. So I don't need to focus more on the physics of these techniques. I'm just going to give a brief explanation and move to the basically different examples I have regarding the application. So the first, starting with the X-ray tomography, so we can use the X-ray tomography to basically look at the microstructure, the internal structure of our system at the micro scale, or in some cases, if we have the capability to look at the nano scale. So if we do just, as shown at the top images, if we do just radiography, similar to taking a radiograph from any part of your body, right? The high absorption, or the darker area shows the higher X-ray absorption, the lighter area of low X-ray absorption. If we rotate the sample and take the images from the different angles, we're going to get the 3D image similar to the CT scan you get from your skull. So obviously after imaging, we have to go through the different process for to analyze the images, the reconstruction. Here I'm showing an example of the air void filling phenomena. So from the left, starting basically the control sample over the time, we have a solution, the salt solution on the top of the samples, and we monitor how the air voids getting filled with the salt solution, right, or any salt deposit. So we can do this reconstruction to get basically idea about the different features, the distribution of the air void, the aggregate, interface, and so on and so forth. But something I developed during my PhD was basically use this interesting technique to look at the mass transfer. So if we can basically take a control sample and have the solution on the top, and non-destructively over the time, I can use the same sample over and over and scan, and from this scan I can get basically the diffusion bond. This is more qualitative, but also I can do a quantitative analysis. So I can basically get the average intensity, and by using some standard samples, I can move from these images, the gray level images, to the concentration profile as shown at the right. If you compare with the traditional conventional method, you have to take a powder rate, you have to analyze by using different techniques, so it's a destructive, it takes a lot of time and effort, but this is just in a couple of seconds you can get a single profile. Regarding the neutron imaging, Jason had a talk in very specifically discussing neutron imaging, how we can apply for different techniques, but this is the overview. Basically, you have neutron source, and from neutron source, neutron beams comes. Basically, it's released to the sample. Part of the neutron is getting absorbed by the sample, and part of it is detected at the backside by detector, right? But the good thing about the neutron, it's very sensitive to the hydrogen atoms, or in other words, if you are interested to look at the water movement in the system, that's a great technique, because if you compare with the X-ray, X-ray have a low interaction with the hydrogen or water, so you can't really observe the water movement. But versus that, if you use the neutron, it's a great technique to basically see the water movement in our concrete samples. This is a facility at Oregon State that I mainly use during my postdoc to do a lot of stuff regarding the absorption and phase stuff, which I'm going to discuss in the coming slides. So from the neutron, as shown at the top left side, we have these grayscale images, right? This is a mortar sample, and then we did the water absorption, so you are exposing the sample to the water from the bottom, and over the time you are imaging, and based on the comparison with the reference sample, what you can do, you can get the water quantity or the volumetric water content over the sample depths with a high resolution around 9 micron. Right? And when we have this, then we can, later on I'm going to show, we can basically obtain a lot of fundamental information about the water movement or filling in the air voids and so on and so forth. The last technique is very useful, is X-ray fluorescence microscopy. The difference between this and the bulk X-ray, the traditional X-ray, also your computer, in this case, basically the resolution is pretty high because of use of the high resolution polycapillary collimators you see at the left side. And so the resolution we can get around 30 to 50 micron. And the other good thing about this technique is we can get, other than the spectrums, we can get images, right, for different elements. So we can map the system. This is a surface technique. So with a small amount of the polishing, you don't need to use any coatings. So you can put your sample, really large size samples underneath this display, and you can image it, this raster you are seeing. For example, you can get the chloride map, you can get the potassium, calcium, and so on and so forth. And then you have these elemental maps from this X-ray technique. What you can do, you can basically combine these different maps and provide a compositional map you are seeing here. So basically, we can separate the aggregate from the paste, and over the paste or the depth, you can see what is the concentration of the chloride or any other ions you are looking at. And you get the profile from this one, and we already basically compared with the titration. There's a good correlation, so it's very useful to look at basically chloride penetration. But the main point, we can see the impact from different features. If you have an aggregate, how aggregate is basically impacts your penetration, the distribution of the cracks, aggregates, and so on and so forth. This is the one application, very quick application on this, use of the micro XRF. So we had different samples. On some samples, we applied the silane sealers, and the other one silane plus epoxy, and we have control sample. So we expose them to the chloride solution, and you see basically after 90 days, the difference in the penetration. So you can see with a high spatial resolution, the impact from this different type of the sealers on your penetration depth. So the first in-depth example I'm going to discuss is the freeze-thaw damage using the combination of X-ray and neutron imaging. So we all familiar with the freeze-thaw damage rate. Basically then our saturation in the concrete pores passes a certain level, your freezable waters increases, you get the expansion rate due to the phase change from the water to the ice, and that causes cracking and spalling, and at the end we have this liability of trillions of dollars of damage to our structure. These are important factors in our durability design. One is the permeability of the system. The other is basically your spacing factor, your failure, the degree of the saturation, and freezing rate. The parameters we're going to focus here, since we are discussing the mass transport and application of these techniques in the mass transport, is going to be degree of saturation, how we can get help to understand the impact from spacing factor as well as the permeability. So typically we use this ASTM 1585 to get the water absorption, but the problem here is this is very bulk method. You don't really understand what is the exact filling rate of the air voids versus the matrix force, right? So you don't have that information based on this technique. But if you use the neutron technique I discussed, right? Again, we are imaging the sample in a controlled manner, and then we expose to the water to get the time-dependent images. Then we can use the Beer-Lambert law to basically quantify over the depth what is the volumetric water content, right? And if we get the sum of this volumetric water content and we compare it with the gravimetric method, which I discussed at ASTM 1585, you see there's a good correlation. So this technique is first, but that's not the main purpose of use of this technique. The main one is basically what we are trying to do here to understand what is the difference between the air void filling and matrix force filling, right? So we developed this simple model. Basically, the start point shown at the left side, it's the initial state when you are exposing your sample to 50% degree of saturation. Then you are starting absorbing water. Then you're going to start absorbing into the basically matrix force as shown at the middle point, right? Middle image. And then at the right side, after some point, you're going to start feeling the air void. So we use or combine this results with the Powers model in order to quantify this over the time. So that's what you are seeing here. At the right side, I have over the time what percentage of the air voids are filled over the time over the depth of the sample. And I can compare this with the total volume of the air you have in the system. And then if I use this one, then I more accurately basically find out what is the absorption rate for the air voids versus the matrix force. So I'm separating the air voids from the matrix force by using this technique. And at the right side, you see the example, one sample with the 3% air void, the other with around 6%, and you see the percentage of the filled voids and the impact from the basically higher percentage of the air void in your system. And the other basically perspective here for the freestyle is the air void filling by the salts, or if you are having a salt deposit inside the pores, how that's going to impact your overall freestyle performance. So in this case, we can use X-ray imaging. I discussed what are the basically background about the X-ray tomography. So this is a paste sample at the left side. We took a radiograph at different angles, then we reconstructed and took these images. As you can see here at the left side, we have the control one, and then over the time we can monitor and basically quantify what is the which size of the air voids and what percentage of the air voids are getting filled with this salt deposit or salt solution. So you can see at the top, mainly the smaller air void system, less than 200 micron getting filled in this system at around 6 millimeter from the surface, and that's going to be basically your supersaturated area, what you are seeing at the bottom graph. So when you have or reach this supersaturation level, your air void is getting filled with the salt deposit. So based on this information, basically we can use this for the modeling as well. This is an independent work done with the Georgia Tech folks, the modeling, and that's the experiment at the left side I just explained. So we are basically confirming each other. You can see the internal air voids with the rate less than 100 micron and get filled within the 60 days at that first 6 millimeter from the sample surface. So really useful data to confirm and to basically your modeling work and provide more valuable modeling techniques for freestyle performance. So this is basically how we can use these techniques to design our materials for freestyle resistant materials, right? So at the left side, we provided basically X-ray, the data from X-ray and neutron imaging, right? So we can play with different air void admixtures, and then we can test with these two techniques, right? Get this information, the feeling, the permeability, all that data, and then we can basically plug in this life cycle estimate and to see how air void quality, what I'm showing at the right side, impact your service life against the freestyle, right? So that's going to be great help basically to account for the spacing, to permeability, and also the degree of the saturation of our system. So the next application I'm going to discuss is internal curing, and mainly I'm going to discuss the use of the neutron imaging. So I'm sure most of you are familiar with the internal curing, so we are providing internal curing through the, in this case, lightweight aggregates. And the point is we can get help to improve the durability of the system or improve the microstructure by using the internal curing. We had a project from... Thank you. We had a project from the ACI Foundation, and the goal was to apply this neutron imaging to see the impact from the internal curing. So we basically build our samples, we tested different curing conditions, and after curing and drying, we exposed our sample to the neutron to get the images. And in this case, instead of basically tracking the free water in the system, we track the bond water in the system. So we dry the entire system. The only thing left is basically your bond water in the system. So if we can look at the distribution of the bond water as shown at the bottom image, right? So this is basically gives you an idea of what is the volume of the bond water over the sample depth. And this can help us to basically quantify the impact from the curing on degree of hydration over the depth. And using that data, we can get impact from the internal curing, right, to understand how that helps at the surface to reduce this curing affected zone, what we call as here. And you can basically compare at the left side, I have different curing times. By increasing the curing time, you are reducing this difference between the bulk of the sample and surface of the sample. And at the right side, you have internal cure system. So you see by use of internal curing, I'm improving the curing or the degree of hydration at the bulk of the sample as well as the cover of the sample. So what we did, we basically quantified this curing affected zone based on the neutron data for different curing times. And that's what you are seeing at the right side for the virgin mix without any IC and the internal cure sample, which is shown in the big blue. So you can see the impact from the internal curing on your curing affected zone. And why this is important, because we want to show if you are using internal curing, you can reduce the amount of the external curing, and that's very important for the practitioners, because they want to see more benefit other than a durability by using internal curing. So that's what we are observing based on this data. So we quantified this data, and we found that basically this equivalency line for internal curing versus the different external curing. And we found that based on this data, in case of the OPC and fly ash system, we are reducing the amount of the external curing by around 50–60%. So that was the observation we had based on this use of this technique for OPC and fly ash system. So I'm just going to move to the conclusion. So we can use these advanced techniques basically to help us to understand and explain the most fundamental observation about the different mechanism, the durability mechanism associated with the mass transport, right? We can combine the modeling with the experiment, right, to get more, predict the service life in freestyle environment for different new materials and for different new admixtures. And also we can understand the impact from the internal curing or any other curing. So to get, in order to sell this new type of the curing to the practitioners. So that's what I have. Thank you very much.